Really delighted to introduce Don Hector. I've known Don Hector as a long-term supporter of the Royal Society of New South Wales, 14 years on council, which I think must be almost uniquely long. But when he agreed to give this talk to us, because we were so concerned about these issues, I discovered far more about him: a chemical engineer, extensive experience in industrial processing, co-founder and director of Reverse Ore Corporation, commercialising minerals technology. He co-founded a Technologies Proprietary Limited, formerly managed Dow Corning Australia, held leadership roles at the Asia Pacific Specialty Chemicals Limited and many other groups, and has been a fellow of the Chemical Engineers. It is a great honour to have Don sharing his knowledge with us tonight on the future made in Australia.
I'm going to talk tonight, as you know, about the future made in Australia, the government policy that has been announced by the federal government in the budget in the middle of the year. This is about really about a $23 billion investment over 10 years to stimulate investment in the private sector, particularly positioning Australia as a renewable energy superpower, value adding to our resources that we mine here, particularly green minerals and green metals, supporting innovation and critical technologies, and to invest in workforce development and regional transition. That's particularly relevant if we're going out of coal, for example. In order to achieve that, they've established a thing called the National Interest Framework, and that really identifies two streams of activity. One is the Net Zero Transformation Scheme, which is focusing very much on renewable hydrogen, green metals, and that's all about getting carbon out of the production of metals like steel, alumina, and aluminium via alumina, and then producing low carbon liquid fuels. The economic security and resilience stream really is about reducing dependence on imported materials like critical minerals, and to try and really add a bit of impetus to our clean manufacturing technologies in Australia, where we do pretty well with some of those technologies that are being developed here. If underlying that, which they don't talk about too much in the policy statements, is that what we're really trying to do here is replace coal-powered electricity generation, ultimately with wind and solar, but via gas. Gas will be a very important component of that. Replacing coal and carbon in smelting technologies, and the two big hitters there are iron and aluminium, and that's because they're very, very carbon intensive. We're also big producers of sulfide-based materials like zinc and copper, but they're not as carbon intensive because you're not reducing the oxygen content of the ore to make the material you're reducing by taking sulfur out, which produces sulfuric acid, which is a valuable byproduct. And then we're looking at the replacing of fossil fuels with electric technologies or things like biofuels, green ammonia and so on. So I'll deal with those as I go through my talk. The program, though, heavily depends on hydrogen, because hydrogen is a component of all of those things above. But when you start looking at generating hydrogen, the big input there is energy. So what is really of fundamental importance is to be able to face these challenges in providing large quantities of energy at the lowest possible cost. So what I'm going to cover tonight, and I'll apologise in advance that I've got quite a lot of dense material that I'll put up on slides. We are going to make this the focus of the Provocations and Inspirations program next year, so we'll be looking at some of these things in some more depth over the next 12 months. But I'm putting a lot of dense material up. If you're not technically oriented, you may not follow it all. I was talking to my wife about this, and she's a psychologist, so she doesn't understand all the mumbo-jumbo I bang on about. And she said, I'd rather listen to you than read your slides. And I said, well, I think most people would rather read my slides than listen to me. So anyway, make your choice. So I'll take a look at energy. Some very brief comments on critical minerals, and then I'll focus quite a lot of attention on hydrogen, and then move on to green metals, and then to green fuels. So, before you start looking at these challenges, you've got to figure out a way that you can compare costs across technologies. And the established way of doing that is a thing called levelized cost. And in this instance, the example I've got up there is levelized cost of energy, but you can levelize cost of anything. You know, you can levelize cost of steel, you can levelize cost of wheat production. It's a matter of determining really agreeing on what the economic parameters are and then quantifying them. So in the case of levelized cost of energy, what we look at there is basically a discounted cash flow analysis. And you take the cash flows, which are capital investment, so that's the initial upfront cash flow, and then you're looking at the operational costs as you go through, the life of the asset, and then maintenance, and then you've got end-of-life disposal, remediation costs, and so on. And you divide that by the total amount of energy produced over the life of the asset. And you can do that then across any technology that's generating energy. Now, it's very important to note that there's some assumptions underlying this that are critical that a lot of people are not familiar with. It's not actually a true cost, but it's a discounted cash flow, discounting at a rate of return that you define. And the levelized cost of energy is actually the break-even market price for a cost that for the cost at this given rate of return. Now, you can alter the numbers dramatically by your choice of rate of return, because a discounted cash flow discounts the cash flows as time goes by, and if you use a high discount rate, it devalues cash flows a long way in the future. Use a low discount rate and it puts them higher. So use a low discount rate and the cost is higher. So people manipulate that shamelessly to support their arguments. Another very important aspect is the capital cost per unit of capacity. And you'll note here that what I'm using this example of energy, it's usually dollars per watt in the case of energy generation. And what I have up at the top there for the levelized cost of energy is per megawatt hour, so there's a factor of 1 million difference. So you've got to be careful you watch your units. But if I look at just dollars per watt, it gives a very good indication of upfront investment. And then you've got a much more complex life cycle assessment technique, which is a really complex way of disassembling the whole of the life of the project and looking at the economic and environmental impact from all the way from mining the resources, extracting them, refining them, right the way through to final remediation and waste disposal and all of those sorts of costs. So let me take a look now at capital costs. And I've just selected a few on which Australia has got a heavy dependence or they've been controversial in the recent media coverage. And you'll note I've highlighted in yellow too, and the reason I did that was that solar PV has been quite controversial with a lot of people banging on about pros and cons, and so in the last election campaign was the whole issue of nuclear power. And the two that I've highlighted here are solar PV at a capital cost currently of $1.37 a watt. So if you take a decent sized power plant, let's take it, for example, a gigawatt. So that's 1 billion watts. So you put a decent sized solar plant in for about $1.37 billion nowadays. That, by the way, is about 3 million panels. So it's a lot. If you look at a small modular nuclear reactor, the bottom line there, you're looking at $28 a watt. So it's very, very expensive. Even if you project out to 2050, solar PV is still on its way down the cost curve. When we started our Gelion battery business, we figured we'd have to compete at $100 a megawatt hour. We now find lithium ion out there at $60 a megawatt hour. So it's really changing. If you just go out and buy a solar panel, you pay 10 cents a watt for it. That's all it costs. All of the other costs in this $1.37 are the power electronics that get it into the grid. So if you go out to 2050, it's still at 65 cents a watt now for solar PV, whereas optimistic costs around small nuclear modular reactors is still around $17. I think it could potentially advance much better than that and come down substantially, but I'd be very surprised if it drops below the nuclear high pressure water reactor, which is in the line above, and that is projected to be at about $10 a watt by 2050, because that high pressure water technology is what everyone uses now, and it's the most well-developed technology for nuclear generation. Levelized cost of energy now, so this is in dollars per megawatt hour. Large scale photovoltaic is 80, and by 2050 it'll be 54. Small modular, 700, probably somewhere 300 to 500 by 2050. So you can see that, and the other technologies are all sitting in between there. So you can see that why people want to go with solar PV, because it is very, very cost effective. Now, if I'll take a look at renewable energy, and I'll make some more comments about cost and so on in a second, because it's intermittent and that's got to be dealt with. If you look at solar and wind, which are the two main technologies used in Australia or under evaluation in Australia, solar has got really two technologies that are of interest. One is photovoltaic cells, which is all the same stuff as we got on our rooftops. And the top left photograph there is a decent sized solar farm. I couldn't tell you how many panels there, but you can see there's a lot of them. The biggest plant that I actually was familiar with was 300 megawatts, and when I was dealing with that about 8 years ago, they had just received planning approval to put a 1 gigawatt farm in Victoria. So they've already gone in at that size. The top left picture is a photograph of a thermal solar unit in Dubai. I have an idea this might be an artist's rendition, but I'm not certain. I pulled this off the Dubai Electricity Authority website. If you see the rectangular arrays of panels at the back, that's all solar PV, I think. I'd be very surprised if that's mirrors. But what you see surrounding the mast is an array of very highly polished mirrors that reflect the sunlight up onto that glowing thing at the top of the column there. And you can get up to very high temperatures there, several thousand degrees C. And what you do with that temperature up then is generally heat up some big mass. So you pump something like molten salt, or even molten sodium, or molten silicon metal, and you pump that up there as a liquid, and you just keep circulating it. You have a reservoir underground that is insulated. You store a very large amount of energy at a very high temperature, and then when you want to pull the energy out of the system, you use that very hot mass to boil water and pump steam through steam turbines, just as you would in an ordinary coal generation plant, for example. But of course, there's no coal, so it's just a turbine, steam turbine. Wind technology is also evolving. A lot of people are very concerned about the eyesores that are presented by these enormous wind towers you see going up. The biggest I'm aware of there have got a turbine span of 150 metres per blade, so you're up at 300 metres, and they can be 500 metres tall. So they are big turbines, and I've seen some of those going in Tasmania, where I used to visit a lot, and they've put a wind farm up there. I don't think the turbine blades are that long, but I think they're about 100 metres. So they're big turbines, and they can generate a lot of power. By the way, when you see those things spinning, just very slowly, the tips are going just below the speed of sound. That's how fast the linear speed of those turbines is. They have problems because birds hit them. Whether or not that is as big a problem or not is not all that clear, but I think it's a problem. So there's quite a lot of people looking at different technologies for wind, vibrating towers, vortices, where you have a turbine that is a radial turbine where the wind gets sucked up through it, and it uses it that way. I'm not quite sure exactly how they work, but there's a lot of work trying to avoid those problems with the big blades. But as I said, the renewable technology is intermittent. They don't generate when there's no wind. They don't generate when the sun's not out, and that happens at night, naturally enough. So the energy storage challenge is actually very complex, because in order to keep the grid stable, what you generally have is a base load that's always connected to the grid, because there's always someone taking power off the grid, and you know what that is. They don't call it base load anymore. The energy market calls it dispatchable load. And what that is that they want to be able to dispatch that constantly into the network. So your storage requirements there is relatively stable, and it's a constant rate of discharge, plus or minus a bit. It's relatively slow, and it's over low periods. So what you want there is a technology that can just deliver that at very low cost. But you also need instantaneous response, because if a big load hits the grid, it can become unstable. Because when you plug your power point in, you've got 240 volts, it's alternating current, the frequency is 50 hertz. If it drops below 240 volts or goes above 240 volts, that's a problem. And what a very specific problem is that if the frequency changes and you've got about a half a cycle that they tolerate, and then it starts tripping out circuit breakers, you start getting blackouts. So what you've got to do there is have instantaneous response that can pump a big load into the rig very, very quickly. Now, you might remember that in Adelaide they put a battery in, that Tesla was the biggest battery that had ever been installed anywhere in the world about 7 or 8 years ago. The purpose of that was just frequency stabilisation, and that battery you could charge up over several days, and you can discharge the whole thing in 15 minutes. Now, when you're bidding into the market to stabilise the grid, you go into into the auction, you bid on the price. If you think there's going to be a big surge, you bid in it at a maximum of about $14,000 a megawatt hour. So that's what you get when you've got a facility like that. Snowy hydro is the same. That's what they use it for. It's to stabilise load and to stabilise frequency, because you can turn it on just by throwing a valve. And I remember reading a few years ago, Snowy Hydro made their entire profit in about 7 days, just by dropping in at very, very high prices. If you're not familiar with how the national energy market works, generators say, I want to be in the market. They get approved to participate, and then they can bid into the market at prices at 15-minute intervals. And it's just an auction then. Whoever wins, deliver the energy at the price they've bid in at. And if you can't deliver, then you pay the difference to the market. So there's a big penalty for overestimating what you can deliver. Storage needs to be close to the market because of transmission line costs. Generally, there's a mix of technologies to deliver that sort of complex solution. And currently, battery technologies in hydro deliver pretty much everything that we have in mind here. But there are other technologies. Here I've got a list of a few of them. I'll just very briefly go over those. I won't go over all of them in detail. Don't worry too much about the LCOE charges. They're important, but that relates very much to what I was just talking about, bidding into the market. So if you, for example, running a flywheel, it's going to cost you $1,000 to $14,000. Then you'd only bid in when you think the price is going to be that high. You might have heard discussion in the last couple of days actually about the threat to the stability of the grid, and that's the big problem that the national market's worried about is synchronisation. So these things like flywheels and synchronous condensers, they reckon are not going to be ready in time when the big power station at Eraring closes. So the main storage technologies now, compressed air, which is pumping air down into big holes in the ground and holding it and then running it through turbines when it comes out. Pumped hydro, everyone knows about Snowy 2. Thermal energy storage, that's basically, as I referred to a minute ago, on with the solar heating of in Dubai and places like that. Lead acid batteries, they're still very, very cheap, and they're very reliable, but they have a whole lot of other problems. Flywheels, big spinning mass, lithium-ion batteries, I'm sure you know about those. Supercapacitors, I won't get into that there, it's very interesting technology. Fuel cells, that's also interesting technology. It's a bit sort of like a reverse electrolysis cell. And then you've got superconducting magnetic materials. Having looked at that, I'll turn now to critical minerals, because it's a bit of a segue into critical minerals because they're very, very energy intensive. But I'm not going to talk about that much tonight other than this one slide. They're a key input to enabling technologies, particularly batteries and advanced metallurgical alloys. And you need those for making magnets that are an important component of wind generators and a whole lot of other technologies. But you need vast quantities of minerals to extract those. And if you look forward at what the market requires in terms of battery capacity over the next 15, 20 years, there is going to be a huge increase in minerals production and a massive environmental impact. So my view is in the long term, batteries won't be the long-term solution. It's a short-term solution of probably 20 or 30 years. If I had to put money on it, I'd say then we'll have a raft of other technologies coming through. It's not even out of the question that small molecule nuclear might be there if they can continue to develop it. I'd be surprised, but it's not impossible. Australia has an extremely sophisticated and well-developed minerals extraction segment in the economy. We're absolutely first-rate at exploration, mining, extraction, first-stage beneficiation and processing. But most of the final stage refining is done offshore. We abandoned our industrial base about 40 years ago, and so we just don't have the skills anymore to do that stuff. But there's other things as well. You need a lot of capital to do that. You've got to ship the materials all around the world. We have this underdeveloped industrial base, and there's a lot of environmental issues which other countries don't care too much about. And that sort of leads into the last comment here about the dominant position of China in critical minerals. They control over 90% of the critical minerals market, and rare earth elements, it's even higher. It's around 95%. With that sort of impact, they can have a major impact on price. So imagine you might want to put in a minerals processing plant in Australia, you put it all up, get it running at say $10,000 a tonne of product, and then China says, okay, we'll teach them a lesson, and they drop a big supply of mineral onto the market at $3,000 a tonne, and you've had it. And that's exactly what happened with the nickel industry here. Nickel was being processed in a very efficient plant by BHP in Australia, and people took it offshore to China and Indonesia. They cut the hell out of the market. They don't care less about the environment in those countries, and they bring a lot of low quality nickel into the market, but that satisfies the needs, and it made the plant at BHP had unviable. So you've got to be really careful with that stuff. Now, I'll turn now to hydrogen. There's all manner of ways of making hydrogen, and I've just put 6 up here. One list I found I think had 10 on it. They all seem to allocate colours. Now, I happen to be colourblind, but I can read. The simplest and in fact the cheapest in terms of processing cost is coal gasification. Pulverise the coal, heat it up, pump some steam through it, dissociates the water, and you're left with carbon dioxide and hydrogen. Off she comes, Bob's your uncle, up goes the CO2, and that's what everyone did for 200 years. Grey is steam methane reforming, which is now the main industrial process, and the reason for that is that there's lots of methane comes off in oil extraction and coal bed methane, and you can take that methane and reform it using steam, which I'll talk about in a little more detail in a moment. Turquoise is pyrolysis of, basically that's exactly the same as coal gasification, except that you're not burning coal, you're burning other carbonaceous materials. It can give you a better outcome because if you use biomass that's quick growing, you can essentially have a sort of a recycling of carbon, and so it's not as bad. Then you have blue, which is steam reforming with carbon capture and storage. Technology is pretty straightforward. You just capture the CO2 as it comes off, compress it, turn it into a liquid and shove it back down the hole that you pull the gas out of. But it's yet to be demonstrated at scale. My guess is it's a very sloppy solution. There's nothing clever about it. Electrolysis using mixed renewables, they can have a variable footprint depending on the generation technology you use. And then you've got yellow, which is electrolysis using PV. Ultimately, people think that's the way that where the market will head up. The last two of those just produces water as a byproduct, and there's plenty of that around, so no one cares too much. Those really are the main technologies under consideration in Australia. So let me just spend a minute on steam methane reforming. What you're basically doing here is you're taking methane and steam and running them over a catalyst at high temperature and pressure, something like nickel or iron. And what you're doing is producing a molecule of a molecule of carbon dioxide and 4 molecules of hydrogen. The best way to do this is to maximise the hydrogen output is to do it in 2 steps. So the first one, you take the methane and react it with steam, but you don't put quite enough steam in there to turn it to carbon dioxide. So it only converts to carbon monoxide, and you can vary the operating conditions to make that pretty efficient. And the output of that is called synthesis gas or syngas. And the big advantages of it is that it's only one single processing step away to convert syngas into methanol. And methanol is one of the biggest demand feedstocks in the world for further downstream production. So a lot of steam reforming plants are not to produce the hydrogen, they're to produce the syngas so they can make methanol. To produce pure hydrogen, you go through another step, and that's called the water-gas shift reaction. So you take another molecule of water and react it with the CO that you've formed, the carbon monoxide, and that gives you another molecule of hydrogen and another molecule of CO2. So the overall reaction is you're taking 2 molecules of water, reacting it with the 1 molecule of methane, and you get 4 molecules of hydrogen and a molecule of water. Of CO2. Problem is that generates, stoichiometrically, that generates 5.5 kilograms of carbon dioxide for every kilogram of hydrogen you produce. And the reason for that is the molecular weights are so different. In practice, the range is between 6 and 7 to 1, but that goes up as high as 10 to 1 if you've got old plant. So you've also got some other complications relating to feedstocks, and the main issue is that what we're using as the feedstock for methane is natural gas, which is generally liquefied natural gas, and it's 90 to 95% methane, which is really good. The other stuff in there is it's usually water and a bit of other alkanes like butane and ethylene and stuff like that. And that's all valuable. They strip that out, and there's other bits of rubbish in there as well, a bit of sulphur and whatnot. But the main problem is that there are leaks during every stage in production of liquid natural gas. It's very difficult to pull it out of the ground without some of it leaking. Liquefaction and transportation process and distribution can amount to several percent. Best practice is a couple of percent. But when you roll it all up, it's pretty typical to lose 4 and 5%. In fact, there was an estimate done in the US gas network a year or 2 ago, and they reckon they were losing 5% of all the gas distributed. And that's a lot, because methane is a big problem as a greenhouse gas. It's 80 times more effective as a greenhouse gas than CO2. That's in the short term, but it decomposes in the upper atmosphere with UV light and cosmic rays and whatnot, and the longer term net effect is about 28 times. And because some of the LNG is burnt to heat the process, that also produces some CO2. The alternatives, there are a number of these, and I'll just briefly touch upon these. One is solar thermochemical hydrogen. You take one of those solar thermal units like the one in Dubai, and you have a reactor up there that has a metal oxide in it. You use solar energy to reduce the metal oxide, so to drop its oxidation state. That gives you half a molecule of water, and then you blow some steam into it, and it takes the oxidation state back up to what it was originally, and it spits out a molecule of hydrogen, and then you just repeat the process. So it's pretty efficient. I don't think the technology is highly developed yet, but it's got a lot of promise. You've also got photoelectrochemical, and that little diagram on the left there is a photoelectrode panel that has an anode and a cathode built into it. You pump water in, you put sunlight on it, and that you get hydrogen and oxygen coming out. I think it's some sort of semiconductor, but I don't know much about the technology, to be honest. And then you have electrolysis, and the lower diagram here is an electrolysis cell, and I'll show you that in a bit more detail in a second. And then you've got photobiological, which is green microalgae and seaweed and stuff like that. But there are certain organisms that can produce hydrogen from that. It'll be a niche market at best, in my view, because of the amount of organisms you need to sustain it. So let me take a look quickly at hydrolysis. This is an alkaline water electrolyzer. There's all sorts of different technologies for hydrolyzing water. This is the most common and it's the most mature, has relatively low capital cost and relatively long life, but unfortunately it's not all that efficient. It's about 70% efficient or a bit more, 75. There are other technologies now that are up around 97% efficient, but they're a lot more expensive and they don't last as long. On this cell, what you're doing here is you apply a potential difference across a membrane, and then at the cathode, you take a molecule of water and you add a couple of electrons to it, and that gives you a molecule of hydrogen and 2 hydroxyl ions. You take the hydroxyl ions, and well, they're sitting in the solution, and because you've got a potential difference there, it forces it across the membrane so that it can't recombine at in that side of the cell. When it gets to the other side of the cell, the hydroxyl ion reacts with water, and it strips the electron off the hydroxyl ion. Sorry, it doesn't react with the water. It strips the electron off the hydroxyl ion, and it produces water and half a molecule of oxygen and 2 electrons. So ultimately you get down to this equation at the bottom. If those are the 2 half-cell reactions, they're actually happening in conjunction. They don't happen separately. And so you've got 2 molecules of water, gives you a molecule of oxygen and 2 of hydrogen. So it's very promising technology, and that's the one that most people are putting their bet on at the moment until the others come through to a greater stage. But there's other complications with hydrogen, and these ones are a matter of physics, and there's not much you can do about them. It's a very difficult and hazardous substance to handle from an engineering perspective. Engineers get the horrors when they're asked to design hydrogen plants. And the reason is that it boils at minus 253 C, which is only 20 degrees above absolute zero. So it's very, very cold. You need very, very high pressure equipment to compress it to that degree. And when you get it down to that degree to make it liquefy, you've got to store it. And the best way to do that is in cryogenic equipment, so you can maintain the temperature at minus 273, so it doesn't boil. But one of the problems is that when you actually have it in a production environment, it has these really unfortunate properties. It's extremely volatile. Something that boils at minus 273 doesn't take long to evaporate. It's odorless. It has a very wide explosive range. The explosive range is the range of mixtures that you have, in terms of the hydrogen-oxygen ratio where it will explode. And what you want, ideally, when you've got a hazardous substance, you want that range to be as small as possible, a few percent. Hydrogen is much more than that. I think my recollection is petrol, I think, is around about 7 or 8% or something like that. Hydrogen, I know, is much higher than that. And that means that there's much more opportunity when it's mixing with the air for it to either burn or explode. It has a very low ignition energy, and that's apparent it's very clear from that would be the case because it's so hard to pull these molecules apart when they're water. So you've got to put a huge amount of energy to pull them apart when they're water. So when they get together and they want to reunite and they ignite, they do it really quickly, and so you've got an explosion. The flame is invisible. Now, firefighters don't like that very much. If you can't see where it's burning, it's a big problem. And it also has an odd phenomenon called the reverse Joule-Thomson effect. And I think the best way I can explain this is, if I blow on the back of my hand as hard as I can, you'll notice that it feels cool. And the reason for that is that I have a very slightly higher pressure in my mouth than on my hand. When the gas goes through the orifice, it cools down. And that's what they use to cool in refrigeration. You've got a gas that's compressed, you blow it through an orifice, it expands and it cools right down. Hydrogen has the reverse effect. You pump it through an orifice at pressure, it heats up. And in fact, if you take a pinhole in a process pipe and you have a hydrogen leak through it, it can heat up to the extent that it'll take the heat of the pipe up to red heat, and then it will self-ignite as it comes out and hits the atmosphere. So you've got to be very, very careful in designing hydrogen equipment at pressure. The other problem is that the density of hydrogen is 14 litres per kilogram. Now compare that to petrol, which is 1.3 litres per kilogram. So you can store a lot more. If I had a cup of petrol here, I could store a lot more than a cup of liquid hydrogen, store a lot more energy. So the energy density of liquid hydrogen is very high, 143 megajoules per kilogram, but that's only 34 megajoules per litre when you take that 14:1 problem into account. So the actual, on a volumetric basis, petrol is more intense than energy intense than hydrogen in liquid form. Now, what engineers worry about is storing things in volumes. They're not too worried about the mass, so they're worried about the volumetric storage. So you've got to have much, much bigger storage facilities for hydrogen than you do for petrochemical products. And that's one reason why petrochemical products, particularly oil, has been so successful. It's so energy dense. Potential solutions, looking at things like liquid organic hydrogen carriers. So if I take toluene, which is C6H5CH3, and I add an additional hydrogen atom to every point on the ring except where the methane group goes off the toluene, I can store another 5 atoms of hydrogen, and you can do that by running it over a catalyst. The catalysts are very expensive. I think they probably use platinum or something like that. Then you've got methyl cyclohexane, and that's quite easy to store. It's about the same sort of flammability as petrol. But it also requires a substantial energy to both hydrogenate and dehydrogenate it when you want to pull hydrogen off. Now then you've got liquid ammonia. It's got a higher volumetric energy density than hydrogen, but it also requires, as any of you have ever experienced ammonia, it requires very careful handling and safety measures. The technology for making it's straightforward. It's old technology. It's well over 100 years old, highly developed, but it's also very intense. There are promising alternatives to Haber Bosch being developed, but they're still a long way from being able to be cost competitive. Then you've got things like chemical hydrides, like ammonia borane, hydrazine. These also are pretty unsafe, well not unsafe, but they're hazardous products. You've got to be really careful with them. The issue here is that green hydrogen is expensive, and I haven't spoken about all of those. I've just took this out of the US Department of Energy report done a few years ago. But you can see there that these technologies here, the established ones like coal gasification and steam methane reforming and so on, and the bar at the right there is the solar PV via electrolysis. And you can see that the costs are really pretty high. And that's got to come down substantially if you're going to really be able to compete. So the real problem that we're dealing with is that oil-based technologies are so cheap. Oil is so abundant and it's so cheap. So let me turn now to green metals, iron and steel first. Am I doing all right for time? Okay. There are three basic technologies to compare here, and the three that I've got, starting from the left, the traditional blast furnace, basic oxygen furnace, very old technology. Blast furnaces, I mean, in some senses they go back thousands of years, but they really got underway in the early 1800s. The blast furnace design that we have now is pretty much the same as it's been for the last 150 years. The current blast furnace technology is absolutely brilliant. It is absolutely brilliant technology. You take iron ore in the top and you put coke there. You use the coke at the bottom of the furnace to power the reaction. The iron ore, which is iron oxide, reacts with the carbon, and carbon dioxide comes off and you have liquid iron come out the bottom. And the real brilliance of it is that it has all of these reactions taking place there concurrently, and the coke provides a framework that holds the iron ore up, and as the coke gradually burns away at the hot part of the furnace down the bottom, it just drops down, and you've got this continuous feed of iron ore, limestone, and that's to take all the impurities away, and the carbon. And by the time you get down to the bottom, you tap the furnace and out comes raw iron. It's fantastic. Problem is, it comes out with a lot of carbon in it, about 10%. Now, that's what pig iron is. So then you have to run it through a basic oxygen furnace. You would have, from your school days, you'd remember this probably as a Bessemer furnace. Bessemer invented in the 1850s, I think it was. It's also very clever technology. Basically what you do is you just take an oxygen stream, inject it into the molten iron, it burns the carbon off, and out the bottom comes crude steel. And what you do is you're basically dropping the carbon content of the steel from about sort of 9-10% down to mild steel sort of output, which I think from memory is about 3% or something like that. So it's a great way to make steel, and it's pretty cheap, which is why it's been such a popular building material. Well, one of the reasons. The two others are called direct reduction iron with electric arc furnace. That's what the acronyms mean. The one on the left, which is the middle diagram, basically uses a slightly different, quite different type of furnace called a shaft furnace. And in this one, you're introducing a reductant, but you're also introducing, you're introducing both an oxidizing agent and a reductant at the same time. You're bringing in the coke, but you're also bringing in some other materials like grey hydrogen to heat the furnace. So what you get out the bottom is also something which has got a bit of iron in it, and you then heat that up in an electric arc furnace, and that together with scrap usually, and that gets the raw steel out. So you've got iron ore and limestone going in the top, and then you've got the, actually that says oxidant agent there, it's actually reducing agent. It's the natural gas and the hydrogen, and that comes out the bottom. Fully green steel, you put hydrogen in at the top, that's the reducing agent. And you get the oxygen coming out of the iron ore, water goes out the top, and Bob's your uncle. But you remember all those problems I identified with hydrogen? Well, try taking all that hydrogen and shooting it into something that's about 1,000 degrees and see what happens. So you've got to be really careful. There's a huge explosion risk and so on. That technology has not yet been well commercialised. There's been a lot of progress though, and as I'll show you in a second, people are very optimistic about the progress on green steel making. And this chart I think shows it well. If you look here, that's where direct reduction with an electric arc furnace is expected to be. And if you look what blast furnace with a basic oxygen furnace is expected to be 0. And they'll be capturing all the carbon dioxide off the old blast furnace technology, and you can see that they're really projecting for that to be quite a substantial change. Important in this too is the scrap element. because the best way, the most sustainable steel you can use is scrap steel, because you don't have to go through the initial smelting process. So we should be recycling every ounce of steel we can just to reduce the carbon emissions. This is Bloomberg's New Energy Finance projections of what steel costs will be out by 2050. I looked up the spot price of steel today. I think my recollection is it's $793 a tonne. So you can see they're saying that it's going to be at the same price as the current spot price of steel. Now, what about Australia? Whyalla is the obvious choice in Australia. It's one of two fully integrated steel plants in Australia and makes about 60% of Australia's domestic construction steel. The other plant is BlueScope at Port Kembla. They're both very sophisticated steel plants and very capable, and they have different roles in life. BlueScope basically makes flat steel, and so they make steel plate and things, rolled steel products like Colorbond and stuff like that, whereas Whyalla mostly makes long form steel, so it's iron girders and railway lines and things like that. And that, of course, is where a lot of the mass goes in steel production, because they're such big pieces. The two plants are different in capacity. Whyalla is about 1.5 million tonnes of raw steel a year, and BlueScope is about 3 million. But as you know, Whyalla went into receivership when the Gupta Group found that they couldn't pay their bills. And both the South Australian and Australian governments have stepped in to provide a rescue package. I'm never a great fan of rescue packages, but I think this one is of very great strategic importance. It's a critical piece of infrastructure for Australia. The plant is very well suited to green steel production because it's right near a high-grade magnetite ore body, and magnetite is, even though the iron content of magnetite is only about between 30 and 40%, whereas hematite, which is what you get up in the Pilbara, is around 60%, magnetite is much easier to process because it's magnetic, as the name suggests. So all you have to do is grind it up into really fine particles, run it over a magnet, and off comes the magnetite, and all the rubbish goes out, and that's essentially the refining process. So you take the magnetite as your ore body. There's a huge amount of renewable resources in South Australia because of the high sunshine levels they have there, and they're already well down a renewables path with solar PV and wind. I found this paper on Whyalla, and they've done some modelling on stepping into on what you could do there. This was done a couple of years ago before the crisis, and they did a model of 365,000 tonnes a year. And they reckon that you could do it for 900 in 2030 and 300 in 2050. That's a bit different to Bloomberg's number. I believe Bloomberg. I don't believe 300. But if that plant can get if they can hold it at 900, and assuming we're comparing like with like here, then that plant would be viable. And you've got to be really careful comparing like with like in these things, because, are they talking raw steel? Are they talking raw iron? Are they talking pig iron? You've just got to be careful to watch what the comparisons are. So let me move on to the second green metal example I'm giving, which is aluminium. And that's aluminium. I'll skip over this quickly. It's very carbon intensive because you use a lot of carbon in getting the aluminium, the bauxite into alumina, and then the smelting process, you'll note here, that it's an electrolysis at high temperature, a few hundred degrees, and the solution is molten cryolite, which is aluminium fluoride, and you mix that with the alumina, and the carbon cathode and the carbon anode makes it very energy intense. They call aluminium solid electricity, and you have molten aluminium come out the bottom. So you can get rid of a lot of the heating costs and so on and with renewable resources, but it's going to be very hard to get rid of the carbon unless you can develop a new type of cell. So much the same challenges there. I'll just skip over very briefly. I was going to say a bit more about green liquid fuels, but I'll skip over it very briefly. Basically, we've got biologically produced fuels, and then you've got liquid energy storage systems like liquid ammonia, which can be used as a fuel, but it's not all that efficient. I'll just highlight a couple of things here. Things like ammonia, if you look at the top left-hand diagram, you can see if you want a lot of power stored for a long time, chemical solutions are a good idea because they're stable. Ammonia is much cheaper to handle, but it has a disadvantage when considered with gasoline or petrol rather, and diesel. And don't worry about this self-ignition thing here. I don't think that's all that relevant. So that's all I'll say about that. Haber-Bosch process, I won't go through this in detail. Basically, you use natural gas as the feedstock. You go through the steam reforming reaction, and then you do the Haber-Bosch process, and high temperature and pressure, very well-controlled technology, very efficient. You can buy cookie-cutter plants. I ring up Bechtel and say, I want a 50,000-tonne plant delivered to the Northwest Shelf in 2 years' time, and they put it on a barge and come and plug it in. It's that good. Emerging technologies, there's a whole raft of them, but I'll skip that. So let me cut to the chase. This is my last slide, you'll be relieved to hear. The big issues, the big issues really are that we have to face here are the low economic complexity in Australia. Industrial sector was largely wiped out in the last 40 years due to laissez-faire government policy on both sides of politics. I think it's an appalling failure of government in Australia. It's an equally appalling failure of business that has no risk-taking capability at all and no investment. They allowed our manufacturing sector to be absolutely devastated and said, bugger it, we're going to become a nation of traders and shopkeepers. And so we import everything and we don't make anything. If you compare that with Taiwan and South Korea, they have sophisticated, complex economies and very sophisticated technologies behind it. I think we've got to start to re-industrialise and build those skills. Skilled migration is a very important topic, and I think we've got to resolve that and have a very sensible debate about it. I'm a big fan of migration. I think it's enriched Australia enormously, but it's got to be done in a way that is well accepted by society. And I think most people feel that way, but they just don't like some of the threats they see at the moment, and we've got to talk those through. We've got to start with preschool education. In my mind, we've got education funding the wrong way round. We should be funding preschool education with a maximum amount of money. Universities, it should all be taken care of by the time you get to university. Fund research at universities and fund education for early education. We need to increase the research funding to universities of the CSIRO. I find it absolutely mind-blowing that a government can say, future made in Australia, and then they have real spending cuts to the CSIRO, which is an absolutely world-class research organisation. It's appalling, and we should all try and do something about it. Similarly, funding to universities. We shouldn't be relying on foreign student income. We should fund them the way other places do. What did America do? They got absolutely ticked off that all the Nobel Prizes were going to Cambridge, and in the 1930s they said, we're going to start funding universities. And lo and behold, they did, and look what happened. I remember once I was on an advisory board at Sydney University for the education faculty. We had University of Michigan Dean of Engineering out. 2 faculties, in terms of income to the faculties from fees and all that sort of stuff, had about the same amount of income. In those days, that's about 15 years ago, no longer, 20 years ago, both faculties were getting $60 million of income from fees and their other sources of income. That's all Sydney University had. University of Michigan, where the visiting dean, they had another $300 million coming in defence contracts. 300 million. That's how America built its industrial base. God knows how Trump's wanting to dismantle it. But, so we've got to really change policy settings to encourage research and innovation, and we've got to lift R&D spending in Australia to at least 3% of GDP. So OECD average is 2.7. We are so far below it. We rank about, of the OECD countries, we rank in the, I think we're the bottom two, in the bottom two. It's appalling. Investing in technology has to be more financially attractive than investing in real estate. But you know, if I'm a professional investor, I can go out and I can drop $20 million on the table, and I know I can get a 10 to 15% internal rate of return over 2 years by putting in a property development. Now try and get that if you're trying to develop some new technology. We need to integrate industrial policy with national security policy. Now, a lot of people don't like the idea of AUKUS. I'm in two minds about it. But boy, if we spend $360 million on building submarines, look at what we've got to do to support that and to do the sustainment work on the American submarines and British submarines that are going to be based here. You know, we're already sending a whole bunch of people over to do training in Britain and the United States on nuclear technology because we didn't have it here. So I think it's a real opportunity. And in fact, one of the companies I worked with, we used to supply the diesel engines to the Collins-class submarine. And that was a very, very sophisticated vessel. It really was. People heard all the criticisms about it, but boy, oh boy, if a Collins-class submarine's around and you're in an aircraft carrier, you better make sure your insurance is paid up. But it's a vast expenditure that's going to take these very substantial resources, and we've got to then leverage that and project them out into the broader economy. And that's all I have to say. Thank you for your attention.
The questions are coming. Thank you very much, Don. Susan, and then behind. Thanks. Is there a mic?
Thank you, Don. You started off with the policy, the new policy. I think you said 40 billion was the figure for the Australian government.
22.7, I think it is.
So drop in the bucket or likely to have an impact?
Oh,
and what do you think of the strategic framework of the policy?
I think the policy itself is a good idea, and I think they're good areas of focus. And bear in mind that I'm not a politician, I don't pretend to be. The money's not enough. I mean, 22 billion over 10 years. I mean, it's supposed to be seed money. I've had some dealings with some of the government seed money organisations, and to be honest, we didn't bother. We just went to private investors and got it.
I want to congratulate you. And I cannot speak strongly enough about the last points you made that are on that slide. And I can't speak too loudly to pointing out the first sentence. And that takes me to the fact that in policy terms, that kind of stuff and the other points you've made are still being argued about. What I cannot understand, with the evidence you've put there, leaving aside other things about, Whyalla and so on and so forth, what is stopping the government developing a compelling argument and promoting it strongly? Why are we listening to that fellow called O'Brien making the most stupid and ignorant comments possible from a party which is responsible for sentence one? And the last point is immigration and the nonsense that's been spoken about, we must stop immigration to reduce the pressure on housing. The housing issues come from the same background. It was asserted under neoliberal policies that we can leave the provision of housing to the market. Can I draw the attention of everyone to the years from 1944 or so to 1955 or so? Now, I'll be quick. The astonishing thing is the government established 2 committees, and those committees had incredibly highly intelligent persons on them, like Nugget Coombs. And there's something or other dwarfs. Just the most marvellous people. And they supported housing, they supported immigration, they supported a whole lot of other things. Here we come to, I don't know if it was 1988 or whatever, and John Howard, but it certainly was Tony Abbott. And I'll just leave the last point. That's also the person who did something in relation to the early lecture here last year by the marvellous former Secretary of the Treasury, who wrote on relations with Asia. On the first day that Abbott became Prime Minister, he junked all of the copies of the reports that he'd been commissioned to write on Australia in the Asian cemetery. And, not satisfied with that, he broke all the IT links.
Okay.
So I support everything you said, and I want you to get this bloody government to promote this. Thank you.
I'll do what I can, Des.
Do you have something more to say about in answer to that question, or?
Look, I don't. I mean, Des and I have discussed these issues many times, and we disagree on many things, but at the end of the day, we agree on most.
Yeah, okay.
Graham, I was hoping you'd ask a question.
Right. Well, I've got about 19 questions, but I'll keep them short. I was in Vietnam about 3 months ago, and everything you have up there is being done in Vietnam. They have a thriving motor car industry. They're advanced on AI. They're across the board. Everything costs 20% of what it costs here. Doesn't matter if you buy a beer or get an airplane ride or whatever. So I'd encourage the Australian government members to go to Vietnam for a month and just find out what they're doing, and maybe we'd learn something. But anyway, that's just an observation. I have a serious problem with hydrogen. I was involved in many pipelines, natural gas and oil, and the biggest problem is hydrogen embrittlement of steel. And the Moomba-Sydney pipeline blew up because of that, but because we had fantastic systems, nobody noticed, which I thought was wonderful. But I was involved in the West Australian development of gas, and they were going to, in fact, create the situation which would have caused serious problems if they didn't understand hydrogen embrittlement. And I think that's the biggest problem, really, is how do you manage hydrogen, how do you get it from A to B, and how do you store it? And I don't know that we've really started to solve that problem.
No, I can't really comment on that. I'm aware of embrittlement problems with hydrogen when you're handling it in steel, but I thought they'd made quite a lot of advances with alloys that can avoid that to some degree. I mean, the Japanese are shipping pretty large volumes of cryogenic hydrogen around the world just to test. I mean, they've done some out of Australia. So I'm not convinced that problems like that can't be solved if you apply the technology. I think the more fundamental ones that I referred to are the real tricks. You know, it's just so expensive to deal with. Yep. So I agree, it's challenging.
Just a question about the green steel issue. I agree. Hydrogen to me sounds like a big problem. The solution of metal oxide electrolysis, I understood there was a fair bit of work going on in that, but I noticed that on the projections it doesn't look like it's going to be a big...
To be honest, I'm not across that technology. I don't know much about it. I know there's a lot of work taking place on electrolysis generally, but I can't tell you what there might be around steel.
Okay.
You mentioned about the discounted cash flow analysis, which of course is the basis of most investment decisions, and particularly in real estate, which you mentioned also. And you said that unashamedly people manipulate the numbers there. What sort of yields are they normally talking about when they're talking about that?
Well, it very much depends on who you are. I mean, if you're a super fund, for example, and you want to invest in something that might have infrastructure or something like that, you might be really happy if it gives you 6 or 7%. But if you're investing as for example, an angel investor in a startup company, and you're looking at the technologies, you might want 40%. So, it's very much situationally developed. If you're a government, you can borrow at low cost relative to the rest of the market, so you can tolerate a lower internal rate of return. So I think when I said people manipulated, I think, in my younger days, I used to work as an economic evaluator, looking at different processes to determine whether the company I was working for would invest it. And I did that for 2 or 3 years. And I always used to go into my boss and jokingly say, do you want to do this project or not? And tell me what answer you want on the internal rate of return or in the cash flow, and I'll give you the internal rate of return and the assumptions accordingly. But we never did it like that, by the way. But, I've seen people manipulate it a bit to swing the balance one way or another. And I was just saying it not because I think people are largely dishonest. I don't think they are. But I'm just saying you've got to be really careful when you're looking at levelised costs that you're using the same parameters. Because say, for example, if you're looking at a nuclear plant, very, very high upfront cost, enormous upfront cost, but it's got a life probably, if you really extend it out, somewhere between 60 and 100 years. Whereas if I look at a solar installation, generally now you've got a service life for solar panels around 30 years, because they decline in efficiency between 1% and 2% a year. So by 30 years they're down to about 60%, and they're not worth generating at that, so you chuck them out. The power electronics, which is the big chunk of the issue, probably has got a service life of about 10 years. So you've got to factor all of those assumptions in your cash flows, and that's why LCOE is so useful, because you can go through the comparison. Say you want to do a comparison over 60 years, you can go through and put all of those assumptions into your model, and if you do that well, you get a very good indication of what it's going to cost you.
Do you think part of the problem also is the Australian banking system, the uniqueness of our banking system with the 4 major banks and their reluctance to lend on anything that's not property based?
Well, I think it's certainly a constraint, yeah. I mean, they're so tied to mortgages. I don't think that's a great thing.
Was there another question
Thank you.
just there? Oh, there's one here. No. Not yet, fine. And then we'll go back.
I'll be very quick because this is a fantastic. I half don't understand because it's so advanced in terms of presentation. Thank you. Just very eye-opening for me. So talking about the key issue, I agree with all of them. But do you think, because I just searched and say who's actually the current Minister for Science and Education, or Science and Industry Innovation, and I searched his background. I don't know who he is, but it returned as the gentleman called Tim, and I asked AI, does he have any science background? AI saying no, he was a trade union officer with Australian Manufacturing Workers Union, and he grew up on a farm near Lismore and studied industrial relations at the University of Sydney.
Yep.
So I wonder, we saw I think people like him or his chief of staff, which are much younger, should probably listen to a lecture presentation as such, so that they won't cut the funding that is actually really silly, but listen to those wonderful presentations. So I think another suggestion, perhaps, if you agree or I don't know, is maybe starting also some education to those politicians of those areas, so that they can actually more understanding of the importance of that.
I think you've put that very well. I happened to hear him interviewed the other day, actually, and I did exactly what you did. I looked him up on Google and found out exactly the same track record.
This is more a comment than a question, but the comment about the banking system triggered a thought which I've long had. You know, people keep complaining about lack of productivity. Well, one of the most unproductive investments I can think of is the fact that we keep pushing up the price of houses. I mean, it doesn't produce anything except more money for real estate agents and property developers.
There was one thing I wanted to mention about that just triggered in the previous question. You might remember about, I don't know, in the 1980s, we used to have banking segregated into property, basic, you know, there were special rules around mortgages, and the commercial lenders were more or less run separately. And then we deregulated the banking industry, and all the banks consolidated, bought up building societies and all the rest of it. And that's meant that our commercial banking sector essentially was dismantled. And if you look at what the United States has done, they took all of the mortgages out of the banking system, basically, and they put it through Freddie Mac and Fannie Mae. So they've got mortgage lenders over there that specialise in that, and they've got a well-established commercial banking and investment banking system that functions more efficiently. So I think it's not surprising that we focus so much on real estate when, you know, you look at all of the banks, and a lot of them have been, at one point or another, building societies.
Still generated the global financial crisis.
Yeah.
Don, just tell me, if you were going to be positive about Australia, where would you hope that we'd be by 2050? With these technologies particularly
we would,
talking about?
well, first of all, I would say I am very positive about Australia. I think we've got every opportunity. All we've got to do is seize it and develop it. I think it's a wonderful country and I love it. And I think we've encouraged migration, and that over my lifetime has brought an enormous diversity to Australia, which I love and enjoy. And we've just got to keep focusing on that and building on that, because it's a real resource. But I think that if I could answer your question, probably I'd say if I looked at a diagram of economic complexity, it would not be just reliant on the minerals sector and 2 or 3 other industries, but it would be this beautifully complex diagram of interacting flows of business and within the economy,
and not just
focusing on niche technologies.
Farms either.
No.
All right. More questions. When we began in 1821, it was not academics. I mean, there wasn't a university. It was very much people who were involved in business, involved in starting Australia, who came together to be part of the Royal Society, people who were working across various disciplines, talking with each other. And I think really, listening to you, I think I'm thinking of a real Royal Society figure, someone who's worked across business, who sees the benefits for Australia and worries about it. I mean, there was a lot that was wrong in 1821. They weren't too good on sending skulls back to Edinburgh and the like, as Alexander Berry did. But there was something there, which is the engagement of our civil society across the board in these issues. And I think that, Don, just your enormous engagement, both in really doing things and then taking it across to the Royal Society. So I think that what I will be saying to you is that the Provocations and Inspirations session, which are on Tuesday lunchtimes at the Union Club, following up this theme, should be really fantastic. And thank you very much. And as I say to our Royal Society champion, thank you.